to the next talk by Pierre Sens, theorist again, models of spontaneous symmetry breaking through mechanical feedback in single-cell crawling.
So I would like to obviously thank the organizer for organizing this great meeting. It has been very, very interesting so far. So I've slightly changed the title of my talk. I will spend half the time talking about mechanical feedback and the other half talking about something else if I have time. So this is the first part. And so this work, part of it will be, which I will describe, is published already, and part of it is sort of still in the process, and the theory is done by Amit Singh, who's here, who will unfortunately soon be leaving for Dresden. And this is in collaboration with the team of Christophe Lamaze and the experiments done by Vibha Singh at Institut Curie for the second part of the first part. All right, so since I'm at the end of this meeting, I don't need to do all these introductory slides. So the question in the first part will be, how do these strongly spatially polarized cells, crawling cells in this case, acquire their polarity, and that is this spontaneous process, or does it require some sort of large-scale signals? So we already have heard several things about excitability. So there are signature of excitability in crawling cells. So there are biochemical waves that propagate. I will not at all talk about biochemical waves. There's also, if you look at the edge of moving cells, for instance, these fibroblasts, you see that although the cell is sort of moving continuously, the edge shows periodic dynamics, which shows that there is some internal activity, or at least dynamical system going into play. And then this movie that Raphael already showed yesterday, which is this absolutely fascinating movie where you trigger the polarization of a keratocyte fragment by pushing on it, which shows that this system was bistable, one stable state which was apolar and another stable state which is polarized. So here again, we've already heard the descriptions of some models that can lead to such behaviors by Pierre and Raphael yesterday, and so I won't get into the description of these models. What I want to tell you about here will be very simple 1D model, and this is a picture of a cell in 3D showing that 1D model might not be so silly. And so you have a 1D model with only two edges, and the idea is that at these edges you will have a mechanical force balance between a protrusive force, which is provided by polymerization of actin, and they're sliding under the action of a membrane tension and atomizing contraction. The sliding will interact with the substrate in some ways, probably specific adhesion, integrin-based specific adhesion. And so this force here will need to be balanced by, or will need to balance the force leading to the motion of the filament, which is the membrane tension and the atomizing contraction. When you write this force balance, that usually leads to the actin retrograde flow dynamics. And then if you put in the polymerization dynamics, then you get the edge dynamics. And when you have the dynamics of the two edge, then you get the whole cell dynamics. And in addition to this, you can also add the fact that some molecules, such as myosin, for instance, could be advected by the actin flow, which I will not discuss. All right, so among the sort of large toolbox that cells could use to trigger spontaneous symmetry breaking and polarization, I first want to focus on the adhesion of sort of friction force, adhesion force between actin and the substrate. And I will be thinking in the context of the molecular clutch model, where these filaments that are sliding here are engaged, but only transiently, with the substrate through bonds that can break. And if you measure using traction force microscopy, if you measure the force created, so the sliding force created by a filament moving on top of a substrate within a cell, you may get this sort of behavior. So this is the force as a function of the velocity. And what you can see is that this force is non-monotonic, so it's linear, like you would naively assume at small velocity. But then in this particular case, it has a maximum, and then it drops. This is only the force on the substrate. And this sort of non-monotonic behavior can be recapitulated by very simple binding and unbinding of elastic bond sort of models, provided that you say that there is some level of mechanosensitivity. For instance, the natural way to do it would be to say that the off rate increases when the force on the bond increases in an exponential fashion, for instance. And if you do that, then you get indeed a force which is non-monotonic, because at low velocity, the off rate is roughly constant, and so you have a linear friction force. But as you increase the velocity, basically the bonds unbind very fast as soon as they bind, and that leads to a decrease. Now, if you add the fact that this filament also has some other friction with the cytoplasm, then you end up getting a non-monotonic force-velocity relationship. And very often when you have spontaneous symmetry breaking models, they are based at one point or another on a curve that has this shape with a possibility of 3 solutions in some range. And that's exactly what is going to be happening here. So if we start with a simple elastic protrusion, meaning that you have this engine here, polymerization, retrograde flow at the edge, and the protrusion restoring force, so the membrane tension would increase as the protrusion length grows, then you have 2 possibilities. One is when the friction force is roughly monotonous. In this case, you have a fixed point, which is when the polymerization velocity balances the retrograde flow, then the protrusion doesn't grow anymore. And this fixed point is stable, and the length of the protrusion will just increase in time and saturate. Now, in the more interesting case where you have a non-monotonic force-velocity relationship, if the fixed point happened to be in the unstable regime, then what you will have is a limit cycle, meaning that the protrusion will grow, the whole thing will slide, the protrusion will retract, and the things will attach again, and you end up having cycles with the protrusion going back and forth. And that depends on some parameters which are related to stiffness, the dynamics of the bonds, and these sort of things. Now, if you look at one cell, which is basically 2 protrusions, then you have 2 possibilities for this cell. The first one is that the 2 protrusions, if you are in the unstable regime, that the 2 protrusions are following the same limit cycle. So the cell is spreading, retracting, spreading, retracting in a very periodic fashion in this noiseless model. And of course, the other possibility is that one edge of the cell remains in the sticking branch, which is the branch which has a high friction, and that would be the front of the cell, and the other end of the cell goes to the slipping branch, which would be the low friction branch, and that would be the back. And if you have these sort of cells, then this sort of symmetry breaking, then the cell will start moving with some dynamics that could be either simple or complicated. The important thing here is that if you look at the force that the cell exerts on the substrate, this force is exactly 0, because the force exerted at the front is opposite than the force exerted at the back, and this is what you expect for isolated cells. Nevertheless, this cell is able to move because the retrograde velocity at the front is much smaller than at the back. And so if you add a little bit of noise in the model, you find out that this sort of symmetric spreading and retracting is likely to be unstable, leading to spontaneous cell polarization. And of course, you can also trigger this by pushing on one end of the cell, in this case, detaching bonds on one end, and that will lead to the motion of the cell in the other direction. And then so you can construct phase diagrams. I won't get into the details, but here, for instance, you have the adhesion strength here and the polymerization force here, and you've got different regimes. So static spreading is stable here, crawling is stable here, and the bistability regime exists somewhere in between. Now, here, what is really important for the spontaneous symmetry breaking is that the 2 ends talk to one another, so that if one end starts sliding, that sort of stabilizes the protrusion of the other end. And in this model, this is mostly mediated by membrane tension, which, of course, propagates mechanical stress from one end of the cell to the other. And what is interesting here is that for the cell to be able to polarize, you need these 2 branches to be accessible. And so if you decrease membrane tension, then only one branch, which is the sticking protrusive branch, will be accessible. And so that means that in order for a cell to spontaneously polarize, it has to be a high enough membrane tension. And so in this example here, we have a cell that spontaneously breaks symmetry. And what happens here is that the membrane tension is abruptly reduced by increasing the cell membrane area. And what you can see is that the cell loses polarity and needs to spread again to a sufficiently high level so that the 2 solutions exist and the cell can spontaneously break symmetry. And the reason I did this was because of this very nice experiment by Kinneret Keren, where she made vesicle fuse with a keratocyte. I'm going to start the movie again. So the keratocyte is very polarized, vesicle fuse with it, and this destroys the polarization of the keratocyte, which starts showing protrusions all over the place until it spreads enough to resume its motility. Right, so this seems to be saying that basically cells will break symmetry and start moving. But you also have many other kinds of cells, so this is probably not the best movies because here cells are interacting with one another. But you have many cells that do not show this very apparent spatial polarization with a clear front and a clear back. And one way to explain this is to say that in these cells, mechanical communication between the two ends is broken by, for instance, by the fact that the membrane tension, which is a way to propagate mechanical information, is sort of not good at doing this. And one way this could happen is because membrane motion on the substrate, for instance, would dissipate energy. And that would happen whenever membrane has a strong friction component with the substrate or with element of the cytoskeleton. And indeed, if you look at motile cells, they typically have a higher tension at the front than at the back, and this is simply, at least one reason for this would be simply passive friction. The front is pulling on the back, but is also dragging on the substrate. And the difference can be quite large. So if you want to model this, then you have to model the propagation of membrane tension along a cell, and you can realize that with using very simple model that it's a diffusive propagation, which means that if the cell front is making a jump, the tension is going to rise really, really high until it diffuses and decreases slowly with a diffusion coefficient that could be of that order. And then in this case, if you have a protrusive, like a periodic protrusion at one end of the cell, the effect of this protrusion will die out over a length scale, which is related to the diffusion coefficient and the frequency of the protrusion. And so for typical frequencies of protrusion, you have a decay length which could be of the order could be smaller than the cell size, in which case those different protrusions would not talk to one another. And then if you do that, you get another kind of phase diagram. So here we've got cell stiffness and the inverse of the friction, where you have different possibilities. So in order for the symmetry breaking to be possible, the friction must be below a precise threshold. And if it's above, then basically you will either have a stable spreading cell or a spreading cell that will not break symmetry but will still have some oscillations. And if you're around here, you can have stable spontaneous symmetry breaking. And then I'm going to be provocative by saying that if you wish to explain these different phenotypes, so the keratocyte polarized, the fibroblasts that sort of throw arms and retract them, or the epithelial cells that spread and do not move, if you wanted to explain this only based on adhesion, then you could locate them in different regions of this phase diagram. Of course, it's too simple, but that's one way you could approach the problem. All right, so let's quickly move into another possible feedback, which would be a feedback between the contractile force due to actomizing contraction and membrane tension. And this work was in part motivated by the observation that but this is from Patrick Caswell's lab, that if you look at moving cells in 2 dimensions in this case, one thing that he noticed is that they have some particular invaginations called caveolae that are much more present at the back of the cell than at the front of the cell. And that they hypothesized from the results that these caveolae would be able to activate actomizing contraction in some ways. And if this is the case, then you could, so these are the results obtained by Viba in Christophe Nama's group, where here they're looking at motility in 3D, so in collagen, and you can see that the cell that contains what it needs to form caveolae, the red stuff, is moving nicely. But if you get rid of some important component of the caveolae, well, first of all, the caveolin, which are this red molecule here, they sort of distribute uniformly in the cell while they are polarized here, and the cell also stops moving. This is the quantification. So the idea now was to say that basically the way you would describe a moving cell would be high contractility at the back, low at the front. That would be an active sort of an active contraction. But also, since the cell is moving, the tension should be high at the front and low at the back. So if you say that tension can feed back on contractility, then you could have a spontaneous symmetry breaking. And the idea was to look at that using the sort of active gel model that Pierre, Recherche, and Raphaël Waitoyer described briefly yesterday. So won't get into the detail. But basically, you have actin polymerization. You have a viscosity here. It's a viscous active model. You have also the contractility due to actomyosin. And you have a friction due to with the substrate, which is what creates the protrusion force. And the membrane also has a friction and a stiffness. And so if now you assume that the contractility has a switch behavior, so it goes from high contractility at low membrane tension to low contractility at high membrane tension, that's this negative feedback here. Then if you just look at the steady state, if you add the restoring force, which is membrane tension plus contractility, then you again find this sort of non-monotonic behavior. Here, this is membrane tension and contractility. At this point, the contractility drops when the membrane tension increases, and that gives you this sort of non-monotonic behavior. So that you can have two possible non-moving states, one with high contractility and a small cell here, and one with low contractility and a large extended cell here. So now if you look at moving cells, in moving cells, the tension will vary sort of linearly from the back to the front. And at some point, this tension will be such that the contractility will move from a high contractility to a low contractility. And the question is, where would be that point as a function of the cell velocity? And so if you work out the math, what you find out is that in order for a stable state like this to exist, the membrane friction, which is this parameter here, must be large enough compared to the cytoskeleton friction. You must be in that regime, which also depends on the cell length. And if you're in that regime, then you will have a stable moving state within some range of contractility jump. If the contractility jump is too small, you won't be able to stabilize a moving state. If it's too large, you won't either, and you will end up with basically a stable non-moving state. And the velocity here will be then proportional to this contractility jump. So very briefly, this is what I wanted to tell you about this mechanical feedback. Of course, there's a lot of work to be done to compare then this with the experiments done in Christophe Lama's group, but this will be for the future. So the first summary is that this mechanical feedback leads to spontaneous symmetry breaking. In the stick-slip dynamics, you need a minimum membrane tension to create the slipping state. And then if you have membrane friction, this will basically impair the mechanism. In the tension contractility feedback, you can also have this spontaneous symmetry breaking, but in this case, this is promoted, and actually it's created by the fact that there is membrane friction with the surrounding and a membrane tension gradient from the cell front to the cell end. All right, so now I move to the second part, and in the second part, I want to switch gear a bit and look at a type of motility where you don't have an obvious apparent polarization, at least spatial polarization in the cells. And so this work was done, the theory was done a while ago by Marco Leoni when he was a postdoc with me, and the experiments were done in Daniel Rivlin's lab by Amélie Godot in Strasbourg. All right, and so I'm going to put these two movies. So this is the curator side. You've seen it many times. And it's obviously spatially polarized, which means that when the movie is played backward, you suddenly say that something weird is going on. And now this is a fibroblast moving in a cell-derived matrix, which means a matrix of fibronectin mostly, I guess. And here, if you play the movie backward, it's a bit less obvious to see which one is forward and which one is backward, because the cell is much less polarized. It sort of throws protrusions all over the place. Also, the interesting thing here is that here the velocity is the same scale than the polymerization velocity. They are both in the micrometer per minute sort of range. While here, the polymerization velocity is the same scale, and the protrusion growth is sort of at the same scale, but the cell velocity tends to be much smaller. So there are two different dynamics here. There's the protrusion retraction dynamics and the cell translocation dynamics. And playing the movie forward and backward sort of rings a bell to microswimmers. So we've heard a very nice talk about microswimmers this morning. So for those who don't know this paper, you must read it. This is Edward Purcell's paper on life at low Reynolds number, where he argues that because microorganisms live at low Reynolds number, where inertia doesn't matter, they have strong requirements to be able to swim. For instance, a scallop, like this guy here, would never be able to swim at low Reynolds number because whenever it would close, it would move forward, but when it would open, it would move backward exactly the same amount, the same space. And that doesn't matter whether it closes fast and opens slowly. This is the inertialess dynamics that basically makes this impossible. It was called the scallop theorem, and basically what that tells you is that with 1 inch or 1 degree of freedom, you cannot swim at low Reynolds number in Newtonian fluids. And so the solution that Purcell came out for this, or at least inspired by the environment, of course, is the corkscrew. That's one thing. So you have a cell body with a corkscrew, and the corkscrew spin in one direction. And obviously, we heard also of E. coli and all this. And so that works because it breaks a time reversal symmetry. If you play the movie backward, the corkscrew turns in the other direction. And so what I would argue is that if you were to look at the trajectory of this cell, not in space, but in a sort of space that characterizes the force distribution that this cell is exerting on the environment, then this would be basically 1 point. It's like a steady state. The thing turns and moves at a velocity that remains constant. It's 1 point with some fluctuations. I will detail what these force moments are in a minute. And I would argue that for cell crawling, this is roughly the equivalent of the keratocyte, which has this constant velocity. I would bet that the force distribution around the cell is moving with the cell, but constant in time. And I would also argue that this is also the same for this compressed cell that Raphael and Anna Maria talked about before. And then there is the other solution, which is this sort of body with 2 flaps in Purcell's language. And here, what he said is that, so here there's 2 degrees of freedom. So if the cell is flapping like this, it's basically 1 degree of freedom. This is like a scallop. It won't move anywhere. On the other hand, if the cell is flapping like this with a time shift between the 2 flaps, then it can move. And if you try to plot this trajectory in the same sort of phase diagram, the synchronous flaps would basically be a trajectory that goes back and forth like this. And the one with a phase shift would be a trajectory that closes upon itself over a finite area. And using simple hydrodynamic model, you can actually show that the velocity of this guy is proportional to the area that is enclosed by this trajectory in this phase space. And so, here I put the model of this chlamydonomas, which is obviously a bit misleading because these 2 flaps are sort of in synchrony here. But here what breaks the symmetry is the fact that the shape of the flagella, when it power strokes, is different than when it comes back. Okay, so it's maybe a bit misleading, but this guy would definitely do a sort of circle here. And what I want to argue with you is that maybe this cell also is doing something like this, and that's why it can move. So let's see how we can get to this. So first we start with the model. So the model is based on 2 dipoles, which are sort of contracting and expanding, which are interacting with a substrate through binding and unbinding kinetics. This binding and unbinding kinetics might be force sensitive, which means that it might be slip bond or catch bond, and there is a phase shift between the 2. So with all these ingredients, then you can get motion. This is the velocity of the cell as a function of the mechanosensitivity. If it's not mechanosensitive, it doesn't move in this case. And so, of course, in order for this thing to move, you need the phase shift to exist. So this is the scallop theorem in some sense, and you need the adhesion to be mechanosensitive. So very quickly, this is so these are the cells that Daniel Rivlin looks at in this cell-derived matrix. And some cells are moving very nicely, and others are moving much less and even not at all. But you can see that these cells, these are also active. And actually, if you look at the displacement of the matrix around this cell, it's the same sort of range than these ones. So it's not like they lack adhesion or force generation. It's just that they're not moving for some reason. And so we didn't do a fancy traction force microscopy. Here what we look at is the rate at which the matrix moves around the cell. And so here you see a clear contraction because the matrix moves towards this dipole. Here, interestingly, you see a contraction at one end of the cell and an extension at the other one. So it's like one dipole contracting and the other one expanding. And what basically is interesting is that if you look at some correlation between the motion of the 2 ends, those cells that are not moving, they have basically no time shift between the 2 ends. And the cells that are moving, they have a systematic time delay between the 2 ends. And so what we did was now to plot this in this phase space, which is the multiple moment of the matrix deformation. So here, this is a dipole. So basically, if the thing does like this, it creates one dipole. And here it's a quadrupole, which is the higher moment. So the quadrupole would be non-zero if one dipole contracts while the other one expands. That creates a zero dipole, but a non-zero quadrupole. And the migrating cells, they systematically show a trajectory that has an open finite area, while the non-migrating cells sort of systematically trace back on their step. And I can show you more examples, but I won't because Jean-François is going to kick me out. I can also show you that some cells can go from migrating to non-migrating, and when they do that, you can see that their trajectory goes from finite area to non-finite area. And we attempted, okay, so this is the model with some noise that reproduces this. Without phase shift, you don't have any quadrupole. With phase shift, you've got this cycle. And you can even attempt to check some scaling laws relating the velocity with the period, but this is very messy, and I won't tell too much about it. Right, so this is the summary. I thank you for your attention, and if you have any questions, I'd be happy to answer them.
Merci.